Title of the talk today is NoSQL Data Modeling. My name is Shtub. I'm head of training at ScyllaDB. And for those that just joined, feel free to write where you're coming from and what you're drinking in the chat window. I'm taking the call from Israel, and I'm drinking some herbal tea. And this is me, as I said, head of training. My background is as a software engineer, and I'm based in Israel, in Tel Aviv. And the agenda, or what I will be covering today, I will start with a quick intro into ScyllaDB and what we do, and also how it's relevant to the talk. Then I will dive into some basic data modeling concepts, which are going to be relevant for ScyllaDB, but also for other NoSQL databases in general, and specifically very relevant for Apache Cassandra and Amazon DynamoDB, but also others. I'll very briefly mention drivers, and if we have enough time, I'll also talk about the read and the write path and compaction strategies, but I'm not sure we'll have time for that. I'm going to be showing you a hands-on demo, so a live lab that I'm going to be running. You're going to be seeing the lab as I'm running it, and then afterwards you'll have a chance to run it on your own. And of course, I want to leave time for your questions. Also, looking at the chat window as I'm speaking, so if you have any questions, if I'm going too fast or too slow, I want this to be as interactive as possible. So feel free to ask questions, and I'll try to check the chat window every once in a while. Great. So let's start with a quick poll. You can answer in your chat window. In the chat window, what's your current NoSQL status? Are you currently using NoSQL? Are you using a SQL database? Or are you just interested and here to learn more? Just so I get a feel for the background of the people that joined today, and maybe I can adjust my talk to what you guys are interested in. Okay, so I see, thank you for answering. I see people with some experience in MongoDB, NoSQL, or Postgres and other SQL databases, and some that want to learn more. Okay, thank you for that. So let me quickly start with an intro about ScyllaDB. Let me go right to the start and talk about the ScyllaDB attributes. So ScyllaDB is an open source database, NoSQL, built for high performance. Basically, it was inspired by Apache Cassandra, and Apache Cassandra is written in Java. ScyllaDB is written from scratch in C++. Some of the key attributes are high availability. So the database works on multiple nodes. In production, it can be between 3 nodes to hundreds of nodes. So I mentioned it's distributed, and that goes together with high availability. Data is replicated across the database to different nodes, and we hold multiple copies of each data. And that means that even if there is some kind of network or hardware or other failure, the database can still be up and running and still serve requests. High scalability, and that means that it's easy and straightforward to scale the database by adding more nodes. So if you have an application that's working right now and you expect it to grow in the future, you can easily scale up the database by just adding more nodes, and that doesn't require any downtime. You can scale it up or down, in a very straightforward way. Also, Scylla is built very close to the hardware, so it makes use of modern hardware. I won't get into that, that's a completely different talk, but using multiple cores, fast networking, sharding, and other things that increase performance, and it's built very close to the hardware. In terms of performance, so this is where ScyllaDB shines. Basically, it's a real-time database for large amounts of data, and where milliseconds, like the performance of queries, is measured in just a few milliseconds, and we have a very low P99 latency, so high throughput and low latency. If that's something that you require, great performance, then ScyllaDB might be a good fit. Low maintenance, so by using ScyllaDB, we can decrease the number of nodes when compared to Cassandra or other databases. And there's no garbage collection or any of those other things that you might be familiar with if you're coming from Cassandra. So it's way easier to maintain. And last but not least, it's a drop-in replacement for Apache Cassandra or Amazon DynamoDB, which means that if you have an existing application running with those databases, you can simply change the underlying database to ScyllaDB, change the endpoint configuration, and you'll get better performance at a lower total cost of ownership. And here you can see some of our customers. I mentioned it's open source. I don't really want to go into these comparisons. You can find them on our website, but let's just look at one. A customer that migrated from Cassandra to ScyllaDB, changed from 40 Cassandra nodes to 4 ScyllaDB nodes, and got results that were 2.5 less expensive with up to times 22 better latencies. You can see more benchmarks and comparisons to other databases on our website. So I don't want to get into that. A few words about the flavors. I mentioned Scylla is open source, it's community-based. You can just click on this link. We'll also be sharing the slide with you afterwards. And you reach our GitHub repository. You can look at the source code, and you can even contribute, send patches, help us. It's a community effort. And of course, that's free for you to download and play around with and use as you see fit. On top of that, we have ScyllaDB Enterprise, which adds some features which are not included in the open source version. And additionally, with ScyllaDB Enterprise, you get our support, 24/7 production-ready support. So if you have an application that's critical to your organization and you want our help with support, then that's a good option. And last but not least, we have our database as a service offering called ScyllaDB Cloud. And as it sounds, you get a managed database as a service. And there you can create a cluster through the user interface. And we will take care of things like upgrading the versions, performance, backups and restores, security hardening, and of course you also get 24/7 support. So that's useful if you don't really want to administer a database and you just want to use it as a service and focus on your core business, which is probably application development and not database administration. And by the way, a key benefit of using ScyllaDB Cloud and ScyllaDB in general is that you have no vendor lock-in. So if you're coming from DynamoDB, you can run ScyllaDB on different clouds, on-prem, like on your own servers, and you're not locked into a specific vendor. ScyllaDB University is our online learning and training resource center. After this talk, probably tomorrow, I will send you a link to the lab that I'm going to be showing you today, so you can run it on your own. It's completely free. You have the link here, but it's university.scylladb.com, and it has quite a lot of lessons, hands-on labs, and material about NoSQL in general, about ScyllaDB specifically. And I welcome you to check that out. The courses are self-paced, so you can do it whenever you have some free time, advance at your own pace. And again, it's completely free. All you have to do is register to use it. I mentioned high availability. I wanted to sort of give an example. So this is something that happened, I believe, around 2 years ago. There was an OVH cloud, cloud provider in Europe data center, there was a fire there, and one of our customers called Kiwi, it's a travel company, was using Scylla, and they had some of their nodes in this specific data center that caught fire, as you can see in the pictures. And Kiwi published a blog about how they maintain their availability by using Scylla, and because they had their data replicated across multiple data centers, they were able to still serve their customers and not lose any data or business because of this fire. Many other websites, as you can see in this quote, including banks, shops, government websites, and so on, went down, but Kiwi remained available. So if that's interesting for you, you can read more. They published an entire incident report. I think you can find it probably on our website, but also on Kiwi's blog. Okay, and that brings me to the main topic for today, which is data modeling. As I mentioned, the things that I will be talking about today are relevant for ScyllaDB, but also exactly as they are for Apache Cassandra, which is a very popular NoSQL database, also for DynamoDB and other databases in this area. So let me start by comparing data modeling in NoSQL databases to relational databases. In relational databases, the traditional way to create a data model is to look at our data, at the entities, the relationship between those entities. According to that information, we create a model or a schema, and then we sort of think about our queries based on that information. So that's how it's done traditionally in the relational database world. In NoSQL, we have to change the way we think about it a bit, and we take into account at the very beginning not only our data, but also the application itself. So usually with NoSQL databases, we're dealing with high performance. And we have to think about the queries that we're going to be using at the very beginning, okay? So we think about what queries my application is going to be using. And after that, or together with that, we think about the data. And only after that, we create the model itself, okay? And I will give a few examples and go into more details, but this is just a very high-level overview of the difference. Great, so some terminology, just so we're speaking with the same terms, and when I use these terms, I want to make sure you know what I'm talking about. So a cluster is basically a collection of key spaces. ScyllaDB can run multiple clusters, but in many cases, it runs a single cluster that has multiple key spaces. A key space is a collection of tables that also defines the replication factor. Now, a replication factor is something that is configurable. It's defined by the user per key space, and that determines the number of replicas or copies that we will have for each piece of data. So in ScyllaDB, as in Apache Cassandra and DynamoDB, data is replicated or copied multiple times to different nodes. And the number of copies that we have is determined by this setting, the replication factor. Okay, so just for example, if we have a cluster with 5 different nodes, and we define a key space with a replication factor of 3, then all the data in that key space will be replicated 3 times to 3 different nodes. Great. A table is basically what's holding our data. It consists of partitions with rows and columns, and the table resides within the key space. So once we define the key space, we can define tables within that key space. And I'm going to show you this in just a second. Partition is something that's related to the partition key and the way that Scylla or Cassandra, for that matter, know where each piece of data on which node it belongs. Okay, so I'll show you that in just a second as well. And finally, we have column name and value. So that's a simple key value pair, and that resides within the row. CQL, which I'm going to be showing you in just a bit, is the Cassandra query language. So we use it with ScyllaDB as well. We inherited that from Cassandra. We made some changes, but basically it's quite the same. It's similar to SQL, which you probably know, but there are some differences. It has what you would expect from a query language, things like create, delete, and alter for a keyspace or a table, and also things that deal with data manipulation, select, insert, update, and so on. I mentioned CQL. There's the CQL shell, which is a way to connect to the database and interact with it, that is run queries. But typically in application, drivers are used and not the shell directly. The shell is more often used for testing purposes and sort of to play around with the database that I'm going to be using or showing you today. Okay, so let's see an example of the Keyspace. I mentioned it's a top-level object that has multiple tables within it, and it controls the replication. And this is how we would define a Keyspace, create Keyspace with a name, Excalibur in this case, and we define the replication factor. In this case, it's 3. Okay, I don't really want to get into that, but ScyllaDB works with multiple data centers. So it's topology aware. You can define multiple data centers and data can be replicated across data centers. This can be done asynchronously as well for performance reasons. And this has multiple advantages. One is performance. So it makes sense to serve a user that's querying the database from the nearest data center just because of the physical location, right? So if it's closer, the performance would be better. And then also, it goes together with high availability, like I mentioned in the Kiwi incident where a data center caught fire. And the third important thing, which is now becoming more and more relevant, is for compliance reasons. So sometimes we want to keep data about users in one geographical region, area. So for example, we can keep the data from all the users in Germany, say, in the data center that's in Germany. Okay, so that might go together with compliance. That's an example of Keyspace. Common data types. I won't read them, but the ones that you would expect. And by the way, I didn't mention it, but we have extensive documentation, and you can find all these procedures, for example, how to start ScyllaDB, how to add a node, how to remove a node, what are the common data types, how to use them. That's all available in the documentation, and that's at docs.scylladb.com. Other than that, we have support for collections. So again, what you would expect, we support sets, lists, maps, and user-defined types as well. I'm not going to get into that, but think about in terms of data modeling, say we have person, and that person might have multiple phone numbers or multiple email addresses, then we might be using collections to store that. Okay, and this brings me back to partition and the partition key. So this is a way of how we can imagine a cluster looks like. In this cluster, we have 3 nodes, nodes X, Y, and Z. And we have here a row, okay? A row has 3 columns, in this case, pet chip ID, time, and heart rate. And for each table, we need to define what is the partition key. Okay, the partition key in this case was defined as the pet chip ID. And what happens when we read or write data to the database is that ScyllaDB would perform a consistent hash function on the partition value, S123 and so on here. And according to the hash, it would know which nodes are responsible for that specific piece of data. Okay, so each node is assigned a range of tokens, of hashes, And according to the partition hash function, Scylla would know which node is responsible for each piece of data. Okay, so I see a question by Anik, and apologies in advance if I mispronounce names. And the question is, when can we expect big data connector specific to Scylla Spark? So there is a Scylla Spark connector. I believe there is a lesson about that in Scylla University, but I know that there is some material on that. And if you ping me later, I can look it up for you, or you can try to find it yourself. Okay, so another question, poll question, just to make sure I'm not talking to myself and that you're with me. Are you currently running a distributed database? And the answers can be either no, or if you are, you can write how many nodes are running in your current database. So just if you can quickly answer in the chat window, are you currently running a distributed database? That is your organization or you yourself, and if so, how many nodes are in that database? Okay, so far I see a lot of people not running a distributed database. And Anik is running a 5-node distributed database. Okay, thank you for your answers. Let's see that people are gonna. Okay, great. So I want to move on to the hands-on lab and show you how ScyllaDB works and talk about data modeling by actually showing you an example. Personally, that's how I like to learn, by actually getting my hands dirty and running stuff. So I'm going to be using an example. We call it the pet care IoT use case. And this is how it's designed. I won't go into the details, but basically there is an owner, and the owner can have multiple pets. Each pet has a number of sensors, and the sensors record different measurements. Okay, so that's the big picture of it. We're monitoring those pets. Let's say you have a dog, and that dog has a collar, and the collar might measure, I don't know, the heart rate or the temperature or any other things we want to measure from our pet. Okay. So let me change to the lab. And this is the lab that I'm going to be running. It's called the Basic Data Modeling Lab. And as I've said, I'm going to be running it and explaining right now. But after this talk, you're going to get an email with a link to the lab on Scylla University, so you can run it on your own. Okay, so what I did before I started talking is I basically ran 3 commands. I'm running a 3-node Scylla cluster on Docker. So I ran this command, docker run. I gave the instance a name, and I gave a Scylla version. And what that did was it downloaded some files because this virtual machine didn't have Scylla before. And it started running the node. And I ran 2 more commands with 2 other nodes, which are pretty much the same. I just added the IP of the first node, so they would know that they're in the same cluster and they would connect to each other. After running these 3 commands, I ran this command called node tool status. Okay, so I'm going to run it again, and running node tool status simply checks the status of my cluster, and I can see that I have 3 nodes. I can see their IP addresses, and I can see that the status is UN. UN stands for up and running. Okay. If it was down or there are different other statuses, I would see it here. By the way, is the font size okay? Can you read the font in the terminal and here on this side? Can anyone answer in the chat window? The font
Yes,
size
we can.
It is awesome. Okay. Great. So I have my cluster up and running, and now I'm going to be connecting to the cluster with the CQL shell that I mentioned before. And I run a Docker command to connect to one of the nodes. It doesn't matter which. In Scylla, all nodes are created equal and they can all serve requests. We don't have the idea of a leader node or anything like that. And all nodes can serve requests, and that goes together with high availability. So I connected to one of the nodes. And if you remember, Keyspace has the definition for the replication factor. And here I define Keyspace called key example with a replication factor of 3. Okay, and using this Keyspace called key example, I'm going to be creating a table. Okay, this table is called heart rate version 1. It has 3 columns, a pet chip ID, and this is the type UUID, time, and the heart rate. Okay, now an important concept is the primary key. Let me first create the table. I just created it, and let's talk about the primary key. So the primary key is composed of 2 parts, or can be composed of 2 parts. One is the partition key, and the second is the clustering key. Let me focus first on the partition key. The partition key, if you remember the slide that I showed before, is the way that ScyllaDB determines which node is responsible for this piece of data. Okay, so selecting the partition key is highly important when you create your data model. And here, I defined in this table the pet chip ID to be the primary key or the partition key. Now that I have this table defined, I can insert some data, very straightforward, insert into table name with the values that I want to add. And you can see that the values are some UUID for my pet, timestamp, and the heart rate of my dog, let's say it's 100. Now, if I want to read this data, I will do a select query, and I can see that indeed my data was written and that it's in the database. Okay, now what happens if I want to add another heart rate value for the same pet? Okay, so let's try to do that. I do another insert. I use the same pet chip ID, but I insert a different value for heart rate, 110 instead of 100. Now, if I read the data, and I try to read all the data in the database, I can see that instead of the database adding the additional row, it actually overwrote the previous row. Okay, so now we only have 1 row and 1 value of 110. So what happened here? What happens is in ScyllaDB as well as in Cassandra that writes are actually updates. So if the value already exists, it's going to be updated. And the way that ScyllaDB determines if the value exists is according to the partition key. Okay, so because we use the same partition key, now we overwrote the data. So this does not really work in terms of data modeling, and we have to try something else. Let's see how we can solve this problem. So that brings me to a compound or composite primary key and to the clustering key. So in the previous example, we had 1 column in the partition key. It was called pet chip ID. There were other columns, but they were not part of the partition key. Now, what happens if I try to query my database according to the partition key and to the time? Can anyone guess in the chat window what will happen when I run this command? So if I run it, querying select query based on the partition key, but based also on another field, the time. Anyone have any idea what's going to happen? Is it going to work? What result will I get? Anyone in the chat window? So Charlene Thomas thinks that it doesn't work. Any other thoughts? Maybe it will work, it'll take some time. So let me help you there. I'm just going to run it, and I get an error request. And the error is that we cannot really run this query without using allow filtering. So basically, this is not really an error, it's more like a warning that says you can execute this query, but just keep in mind that if you do that, we're not really sure about the performance. So we're going to block it unless you add the allow filtering term. And why does that happen? So I mentioned that the database knows which node is responsible for each row according to the partition key. But if we ask the database for a query and we don't, we add fields that are not in the partition key, basically what ScyllaDB would have to do is do a complete table scan and scan our entire data to find the right piece of data. Right now, we just have one row, so it's not a problem. But imagine running, I don't know, 100 terabytes of data on 100 different nodes, and you can imagine that it might take some time and require quite a lot of resources from our database. So what can we do to provide a better solution? We're talking about the data model. What we're going to do is we're going to define a new table, but this time we have the same columns, chip ID, time, and heart rate. However, this time we define the primary key to be 2 columns instead of 1, and they are the pet chip ID, which is the partition key, and time, which is the clustering key. So let me run that. Okay, so let's talk about the clustering key. In each partition, there might be multiple rows, and those rows are ordered according to the clustering key. So they're going to be ordered according to the time in this case. And by the way, clustering key is also referred to as ordering key in some other databases, but it's basically the same. In DynamoDB, it's called ordering key, which I think is actually a better name. We inherited the name clustering key from Cassandra. So I created this table. I have the partition key, chip ID, and the clustering key, which is column time. And now if I insert some data, I insert data in the same way. And this is how data is partitioned. I already went over that. I think we can skip it. But as I've said, the clustering key is responsible for sorting the rows within the partition. And each table needs to have at least 1 column in the partition key. So we have to define a partition key. It can be 1 column or more, but it has to be at least 1 column. However, we don't have to define the clustering key. So the clustering key can be 0 or more columns. Okay. And now if we try the previous query, which is to query our data according to the pet chip ID, but also according to time. And here we provide a time range. We can see that this query is successful. And it's also running very fast. Okay, so for that, you have to believe me because we don't have terabytes of data, but this query is very efficient. It simply runs the partition hash function on the partition key, and it knows which node is holding that data. And then for that partition, it sees exactly where those relevant time fields are, and it knows how to get to those. I'll show you this in a sort of image in just a second. And in addition to making it more efficient and being able to query according to the time, now we also solve the problem of overwriting our data, right? Because now the primary key is defined by 2 columns, so we don't overwrite data when we have the same chip ID. Okay, so let's look at a bit more advanced examples. I mentioned that the partition key needs to have at least one column, and the clustering key can be 0 or more columns, so it's not mandatory to define it. However, we can define each of those keys to be multiple columns. So let's look at this example, heart rate version 3, this table I just create. It has the same almost the same columns. So in addition to pet chip ID, time, and heart rate, it also has the pet name. And the primary key is defined as the pet chip ID, the time. So these two columns will be the partition key, and pet name will be the clustering key. Okay, so now if I insert some data and query, it's going to fail again. What happens here is that if we define a partition key to be more than one column, then when we query the data, we must provide all the different columns that are identified in the partition key. Okay, so what Scylla does again under the hood is it takes the partition key and it runs the hash function on that partition key, and that's how it knows which node is responsible for that piece of data. But if it doesn't have all the data it needs in the partition key, it can't really do that. So it would require, again, a full table scan, and that would be very inefficient and costly in terms of performance. So let's try again, this time with the full partition key. And that works and is also efficient. You have to believe me with regards to the efficiency. And in a similar way, we can define a table with multiple columns in the clustering key, as we do here. So here we have the pet chip ID as the partition key and pet name and heart rate as the clustering keys. And again, we can query according to the clustering columns in this case. So let me run this query just so you see that it works. And some fine details about the clustering and the partition key. So if there is more than one column in the clustering key, in this example, it was pet name and heart rate, then the order of these columns matters. That defines the clustering order. So they would be ordered first according to the first column defined, pet name in this case, I believe. And then afterwards, according to the next one, which is heart rate. So the order matters. And as I've said, all the rows within the partition are ordered according to that specific order. And it's also possible to define an ascending or descending order, right? So if you care more, if you know in advance that you're going to care more about the last items in the order or the first ones, you can define the order accordingly. So when we query, we have to provide the partition key, but we don't have to provide the clustering key. The clustering key is optional. However, if we do provide the clustering key, we have to provide the data in the order that it was defined. We can't just give a random order. And I mentioned the sorting order, so it's possible to do it ascending or descending. By default, it's ascending. Let's look at a quick example. So I define a table here, pet chip ID and time. However, I set the clustering order to be according to the time, but descending. So let's say that I know that my application is going to query according to the last 3 minutes, say. Let's say the sensors are writing data every second, and I'm mostly interested in the last 3 minutes. So I would create an order by descending. And let me quickly run this example, insert some data. And then because we're, let's say we're interested in the last 3 results, we could very efficiently query this data by using this command. So I select from the table with a given pet chip ID, and I limit it to the last 3 results, right? So if you imagine it, Maybe I have it in an image that could better explain it. Okay, so this is how it would look like. Let me enlarge this a bit. So this is how we can think about the data on the node. This is an important image. Think about the partition. So each pet chip ID has is actually a partition according to the pet chip ID. But for each partition, we have multiple values, and these values are sorted according to our clustering key. So I believe the clustering key in this example is probably the time. So it would be according to, if we look at the previous example, it would be according to time, but in a descending manner. So very quickly, we would find this partition. We simply run the hash function, and we have it in a constant time very quickly. And then we have our data ordered, sorted by time, and it would be very easy to query the data. Let me see if there's anything else I wanted to mention here, because I want to move forward. Okay, maybe just a quick summary to sum up the lab. So when we choose a partition key, we want to aim for basically two main things. One is high cardinality, and that means that the range of the values are mostly unique. So here I use the pet chip ID, which I assume is unique. And we also want to create even distribution of the data, right? Things we would like to avoid is low cardinality, a hot partition, and a large partition. A hot partition is a situation where our application, in this example, say, is only interested in one specific pet chip ID, right? If there's a dog that has one chip ID, and the application is constantly querying for that specific dog, then we would have one node that's serving a lot of requests, while others are not serving requests at all. Another thing we want to avoid is a large partition, and that goes together with cardinality. So if this specific pet is going to store a lot of information, we might want to think about a data model which distributes the data differently. So let me give you some examples. Typically suitable partition keys would be a username, which is quite unique, user ID and time going together, sensor ID like we used in this case, and so on. And ones that are likely to be inadequate are, I don't know, say the height of a person, the age of the person. If we're talking about people, say, in the United States, then state is probably not a good partition key. A favorite sports team, and so on. So let's talk about one of those examples to better understand it. Say we're talking about states. We have people, and one of their fields is which state they're from. Then that's probably not a good partition key because some states are quite big. Say California has millions of people, while other states are smaller and they have just hundreds of thousands of people. So the data won't be distributed equally. And additionally, maybe we would be querying more about people from a specific state and not another state. So that can create a hot partition, and the case where some of the nodes are overloaded, while some other nodes in the database are hardly working at all, and that's a waste of resources. Okay, so looking at the chat window, there is a question, where do we define the hash function? So we don't define the hash function. The hash function is built into the database. I believe it uses Murmur 5. Maybe there's a way to change that, but you don't really need to touch that. That's happening under the hood, and ScyllaDB or Cassandra or DynamoDB take care of that for you. I'm just mentioning it so you understand how it works under the hood, but you don't need to do anything with a hash function. Okay. And I think that's it for the lab. Let's see if there's anything important here. So I mentioned the data modeling is query-based. If you saw here what I did in the lab is I thought about the queries and about the application, and only then I thought about how to create a table. Okay, so this was an example, but you can think about an entire application where you think about the queries, the performance required, and then you think about the data model. I mentioned that the primary key is composed of the partition key and the clustering key. The partition key can be one or more columns. The clustering key can be 0 or more columns. The partition key, once it's defined, all the queries need to provide that data. While for the clustering key, it's only optional to provide the data. We try to achieve even data distribution when we create the data model, and for that, it's really important to select our partition key correctly. And the selection of primary key, which includes the clustering key, is very important for the query performance. And maybe one last note is this process of data modeling is not linear. It's not. It's usually more circular, like you see here. So usually you start with the application, you create the data model, you do some performance testing and measurements, and then as you see the results and as maybe your application changes, you might want to change the data model accordingly. So it's something that's constantly changing and alive. One of the benefits of using NoSQL databases is the flexibility of the data model and of the schema, and changes can be made rather easily. Great. Let me see how we are with time. So let me take just maybe 5 more minutes to talk about the read and the write path, and then we'll take some questions. So the read and the write path is what happens again under the hood when data is written to ScyllaDB or Cassandra for that matter. And I just want to show you how everything connects and what happens when we read or write data. So here we have a 5-node cluster, and here it was defined that the replication factor for RF is 3. And that means that each piece of data is replicated across 3 different nodes. Okay, a client wants to write a piece of data, call it 1. It sends that request to one of the nodes. As I mentioned, any one of the nodes can receive requests. All nodes are created equal in Scylla. In this case, it's node V. The client sends a request. Node V would run the consistent hash function on the partition key of data 1, and it would see that in this example, nodes W, X, and Z are responsible for this specific piece of data. Node Z would then send the write along to those 3 replica nodes, and the nodes would write the data. You can see it's added to their data storage. And then the nodes, those 3 replica nodes, would send an acknowledgement back to the coordinator node, to node V. And in this example, for some reason, say there's a network failure here, the acknowledgement from node X to node V does not pass along. And here we have something called consistency level, which I didn't really talk about, but consistency level is something that can be configured per query, and that defines the number of nodes that need to acknowledge a read or a write request for it to be considered successful. So in this case, the consistency level was defined as quorum, and that means that 2 out of 3 nodes need to acknowledge the request. And for that reason, this request will be successful, and node V will pass along an acknowledgement back to the client. So again, RF is the replication factor. It's 3, it's the number of nodes that will, it's the number of replicas that we hold of each piece of data. And CL is the consistency level, which is how many replicas need to acknowledge a query for it to be considered successful. Okay, so in this exact same example, if the consistency level was defined as all, that would mean that all 3 replica nodes need to acknowledge, and then node V would not return an act to the client. It would be considered failure and other things would happen, but that's out of scope for this talk. You can read more about it on Scylla University. And what happens if the coordinator node goes down? Then the client would simply connect to another node and send that request. In this case, the coordinator node is not even a replica node, so it doesn't really matter. But an interesting question is what happens if one of the replica nodes is down? And then that goes to availability, and then it depends on our replication factor and on our consistency level. Okay, I don't have time for compaction strategies, and I want to leave time for questions. Before I do that, this is the link for Scylla University, university.ScyllaDB.com. I'll also share it with you by email probably tomorrow. We have a community forum, that's forum.ScyllaDB.com. And that's a great place to network with colleagues, to ask ScyllaDB related questions, share your use case, or if you want to help and develop a feature. I mentioned ScyllaDB is open source, so you can ask questions on the forum and there's discussion there. This is the link to ScyllaDB Cloud, cloud.ScyllaDB.com. I didn't mention it, but you can start a free trial cluster. With just a few clicks, you can get a running cluster and run different labs on that cluster. So you're welcome to check that out. And last but not least, we have the P99 conference happening in October. It's a virtual event. It's completely free. We have some interesting speakers from different companies, and it deals with basically low latency, high throughput, performance optimization, some really interesting talks. So you're welcome to register and save your spot. I mentioned it's free, and I hope to see you on the P99 conference. And that leaves just a few minutes for questions. So let's see. So there's a question, if I understand correctly, basically about rollback of other nodes if it fails. And what happens with ScyllaDB if there's a failure? There are different anti-entropy mechanisms that are built into the database. And there is something called hinted handoff, which means that if, going back to my example, say the coordinator node needs to write this data, but it notices that one of the nodes, the replica nodes is down, then it keeps this data and using a mechanism called hinted handoff, it will wait until the replica node is up and running, and then it will resend the write to that node. So asynchronously, it will write the data to the node. There are other mechanisms for anti-entropy, things like repair and so on. It's quite a complex topic. It's covered in Scylla University if you're interested. Let's look at other questions. So there's a question, will the nodes redistribute data to an unacknowledged node in case where quorum is met? So the coordinator node will distribute the data to all the replica nodes, okay? If it does not receive an acknowledgement back, then it does not know if the write was or read were successful or not. And there will be anti-entropy mechanisms which will later verify that. But whether the query is considered successful or not depends on the consistency level. And the consistency level, we have something in ScyllaDB called eventual consistency. And that means that data will eventually be consistent, and it might take some time because that's the nature of distributed databases where we're running on multiple nodes. But the consistency is eventual and it's also tunable. So maybe just to give you an example, say that in the care pet example that I showed you before, we're writing information from our sensors every second. So every second I'm writing the heart rate of the dog. So maybe that doesn't need to be really consistent, right? Even if we miss 1 second of the heart rate, it's not a big deal. So there we might use a lower consistency level, say consistency level 1 or quorum. But maybe when we read the data, or if we're talking about, I don't know, a banking application, then we require higher consistency, and then we can set for that specific query. Even though it's in the same application, we can set for that specific query a higher consistency level. So different queries within the same cluster, within the same application, can have different consistency levels. And if you're interested in the topics of replication factor and consistency level, I recommend you check out the architecture lesson. There's quite an extensive architecture lesson on ScyllaDB University, and it covers all of that. Let's see if there are any other questions. I see something about work opportunities. So by the way, we're hiring at ScyllaDB. We're looking for talented people. So if you're looking for a job, you can shoot me an email or look at our website. Let me share my email with you on the chat window. Simply guys. So there's another question, and the question is, can we set multiple coordinator nodes like a slave coordinator? So a coordinator node is defined as a coordinator node just for that specific operation. So again, all nodes are created equal. We don't have any master, slave, leaderless, leaders, any other name you want to call it. All nodes are created equal, and also all data centers are equal. So if the client in this example sends the request to node V, the node V will be the coordinator node for this specific operation only. For the next operation, the client might send a request to node W, and for that operation, node W will be the coordinator node. Let's see if we have maybe one last question. Okay, so there is a good question about transactions. So we do have a notion of something called LWT, or lightweight transactions, and there you can have transactions more in an SQL set of mind, I guess. But that's a big topic. You can look on the documentation or Scylla University about lightweight transactions and how that works. Basically, you set a condition, and only if that condition is met, you actually perform the write. Another relevant thing is counters, which can also be transactional in the SQL asset sense. And all of this again goes with high availability. So with that, we're pretty much out of time. I hope you enjoyed this talk. Feel free to get in touch. I will send you an email with the lab that you just saw so you can run it yourself. Check out Scylla University, join P99. And thanks for joining. I hope you enjoyed it.
Thank you very much, Guy. It was a pleasure to have you here. Thank you, everyone, for coming. See you at our next meetup.